All right, so today's lecture is on induced electromotive force and the electric field. So we're going to start with a loop. Okay, and we're going to make it as circular as possible. Okay, in fact, we want a circular so it has this radius r. Okay, and it is in a magnetic field. Okay, but this magnetic field now, okay, is not just a magnetic field, but it varies. It is a variable electric field. It varies, and we're going to give it a function of 2 Teslas per second t. Sorry, I shouldn't have put that there. Okay, that the magnetic field is now a function of time. And it is changing by 2 Teslas per second. All right? Now, if that's the case, then now also, if it's changing per 2 Teslas per second, that means it's changing in which direction? Okay, well, if our x's are into the page, then it's changing into the page, right? Okay, so that's going to make our current go in which direction? So our fingers, remember, we want our fingers to be inside the loop, right?
Clockwise. Clockwise. Counterclockwise. Clockwise. It's clockwise. Inside. Boom.
Wait.
It's clockwise. It's clockwise. It's clockwise. It's clockwise. It's clockwise. I bet too. $5.
I'm not making money on this. I'll be so happy.
If we remember from Lenz's law that the induced current comes in to counteract the change of the magnetic field. Our magnetic field is pointing up. And so, if we have a particle at this point, the force that is going to exist on this particle is going to point in that direction. And then if it's here, it's going to move that way, right? Okay, this would be counterclockwise. Okay, so I'll take my farm now, thank you. For those of you that bet the farm on you. Okay. So the change is going to be up out of the page, because if we're increasing this way, if we're increasing that way, then the induced current is going to counteract the change, which will be in this direction. And for it to go in that direction, it has to go fingers up, curls around, grab the wire. Okay, the current goes in that goes in the counterclockwise direction. So all of these experience a force in that direction. Okay, now if they are moving in this direction, so remember that our EMF then is equals negative phi dt. Okay. But what is phi based on? Okay, phi. Okay, is B dot A, which is our area, right? So in this particular case, our phi is going to equal, okay, and I'm going to drop the units for right now just for just for some simplicity's sake, drop these units. Don't do this. Never drop the units on your test. I'm at the point where we've done all these lectures. I'm finally going to drop the units. Okay, our field is 2t, right? 2t. Okay, times the area, but what's the area of this loop?
Pi r squared.
Is pi r squared. Okay, so our phi is equal to 2 pi r squared times time. Yeah? It's times time. All right. Well, if this is what our phi is, and our EMF is negative d phi dt, okay, then this is negative d dt of 2 pi r squared times time. Yeah? Okay, well, what's that going to be? Our EMF equals negative 2 pi r squared. Okay. Now, that means that our delta V, okay, or we've learned earlier that our delta V is also equal to, gosh darn it, delta V is equal to our field times our ds, right? Remember this one? Yeah, we're setting the Wayback Machine here. I get that. Okay, or actually we're setting it to yesterday. Didn't we have this yesterday? Let me check my notes here. No, not quite. No, we didn't do that one yesterday, but it's there. Yeah. But if we go all the way around this loop, doesn't this become a line integral? Okay, where this would become our EMF and our E is equal to and this is an exceedingly profound statement. This is the actual complete Faraday's law. Okay, yes?
Why did you need a formula for E if you didn't use it?
Sorry?
Why does the EMF have to be negative 2 pi r squared if it's not in that law?
Just for fun.
Well, sorry. Let's try, I didn't work it out. What is the ds going to be right here? Okay, so, right. Right, circumference, which would be how much? 2 pi r. Okay, and so our charge, okay, so if our field, okay, is going to be based on our field is going to be based on the distance from the charge, right? Which would be the other r. Yeah?
Yeah.
Okay, so that's where this is coming in. It's to show the relationship of the 2 pi r and show that that's the ds. Okay. If you integrate 2 pi r, you get pi r squared, which is the area. Yeah. Okay. Which is the other way of thinking about it conceptually? Is that if we're integrating this, we get 2 pi r, right? But if we're taking the derivative of this, that's related to the area, right? Okay, well, the time kind of, but Okay, but that's how they're getting these related. Faraday did the hard work. Okay.
Does S and T cancel out on top of
S and T.
the very top?
Yes.
So S stands for second.
Yeah, Teslas per second. Yeah. Okay, this is the complete Faraday's law. Okay. All right, so that gives us Faraday's law, but here's the idea. What I didn't do a very good job of getting across. Before, when we looked at this, that our voltage equals our E dot ds, that's usually came from the electric field coming from a point source. Okay, or at least some Gaussian surface that we could treat as a point source. This is not that. We do not have a point source. This is an electric field that is being created by our magnetic field. Okay, and it's through this loop of wire. And so what this essentially does is it's creating a loop of electric field with our moving charges. You follow? So if it's just some kind of conducting wire, the magnetic field induces a current. Okay, the current wasn't there before. In fact, there probably wasn't even a charge on the loop. Okay, but when the magnetic field hits the loop, then we start charges moving. And now all of a sudden we have a significant amount of charge that is being moved, and that is creating our electric field that's traveling around. Okay, so that's where we go from our E dot ds to our line integral E dot ds, okay, around this circle. Okay, and this is caused by, okay, and is directly equal to the change in the magnetic field. Okay, that's what Faraday came up with. Okay, and this is the last then of our equations that James Clerk Maxwell compiled, and we call these the Maxwell's equations. Okay, so we start with our electric flux. And the electric flux was equal to, okay, the line integral of E dot dA, which equaled Q enclosed over epsilon naught. Okay, and this is how we start determining the electric field for an isolated charge. Okay, so this is E for an isolated charge. Okay, we have the other one. Okay, the magnetic version of this is B dot dA. However, this equals 0, and this equals 0 because there are no, and this tells us that there are no magnetic monopoles. Okay, that there's no magnetic monopoles, that there's no magnet that exists by itself that creates, or there's no north end or no south end that creates a magnetic field around it. That all of the magnetic fields, if you follow the area, the change in the magnetic field over the area that it's covering will always loop back into itself, and so the amount of field out is equal to the amount of field in, so it's always 0. All right, then we have, in fact, let's zoom in on this a little bit. Then we have B dot ds, okay, which was the Biot-Savart / Maxwell Faraday's, no, the Ampere Maxwell, all that sort of stuff, all rolled up into one. where we have mu naught equals I enclosed. Okay, but we also included on this that we could have an implied magnetic field. An implied current, not an actual current, but an implied current, which was mu naught epsilon naught times the rate of change of flux. And this is where we had capacitors. Okay, the capacitor, we had a rate of change of electric field rather than just the current itself, which technically is a changing electric field as well. Okay, so this one led to magnetic fields come from currents or a changing electric flux. Then we have our fourth one. Okay, and this is our voltage equation. That our voltage equals the integral of E dot ds equals negative d phi b dt. And this one says that a changing a changing electric flux gives us a magnetic field, and a changing magnetic flux gives us an electric field. Okay, and these all together you put on the front of a t-shirt, okay, and you say, "Let there be light." Right? I think Sheldon has that t-shirt. I've seen it around. But these are the Maxwell's equations. And the cool thing was you have this mu naught epsilon naught. You take 1 over the square root of that. That gave us that defined what the speed of light had to be. Okay, and a whole bunch of other cool stuff. Although we don't solve for why that defines it to be the speed of light, but that is the speed of light. It's 1 over square root of mu naught epsilon naught. So these are the Maxwell equations. These are the equations that pretty much completely govern all of electricity. If you want to win a Nobel Prize, raise your hand if you want to win a Nobel Prize. Okay, about half of you. Good. Okay, we'll work on the ambitions of the other half of you. Okay. If you want to win the Nobel Prize, here's what you do. Extend these to include gravity. Extend them to include gravity and quantum mechanics. Piece of cake. Right. That would be the grand unified theory, or the GUT, okay, also known as the theory of everything. And this is not the movie that we're talking about. This is not the Hawking movie, although that's what he tried to do. And yes, because that's why you win the Nobel Prize if you get it to work, because you'd be the first.
I want to win the Peace Prize.
So we just have a couple more topics to cover next week, and but these are the topics that govern all of our electricity and magnetism. Question?
On the bottom right, the C, is that?
This is B. Yep, phi sub B.
Why is mu not? Why does it not need to be experimentally confirmed? Why is it like?
It was defined. It was defined as a particular value in order to allow for the unit of
Like a constant proportionality?
yes.
Oh, okay.
Yeah. Okay.